Hello students, welcome to the amazing platform of Physics Wallah. Welcome to the PW English channel, my dear students. We have reached on the third lecture of surface chemistry. Till now we have covered a lot of things. We have found the difference. What is adsorption? What is absorption? How can we classify adsorption? We can classify it into physisorption, that is physical adsorption, or chemisorption, which is chemical adsorption. Later we discussed about the colloids, how your colloids are classified, also how we can prepare the colloids. Okay, also we practiced a lot of questions based on those, my dear students. Today we are going to cover colloids as well. Only we will be covering how, now once you have prepared colloids, obviously there will be some impurity, right? How can we purify those colloids? This would be the major topic of today's class. So let's start the amazing session, my dear students. So topics which we are going to discuss is purification of colloids and emulsions. Okay, so let's start the amazing session. First, my dear students, the purification of colloids. How can we define purification? The process of removal of impurities from colloidal solution is called purification. Obviously, you have a colloidal solution where there are a few of the impurities present. How can we remove them? That is the major role, and this is known as purification of colloids. Okay, yes, so if you want to write the definition, please do write it and then we'll move forward. Okay, perfect, please write it down. I hope you've written it. Now let's move forward. Now, my dear students, we'll be discussing various methods of purifying colloids. Okay, so now the first and the most easiest is by dialysis. How can we purify it by dialysis? First, let me explain you and then we'll read the theory part. Okay. So now, my dear students, when we talk about colloids, they have some impurities, and let us assume the impurities are crystalloids. That is, their size range is of true solutions. Okay, so you have a colloidal solution whose size range is between 1 nanometer to 1000 nanometer, and you have impurities present in it which have the size range of less than 1 nanometer. Okay, so now you need to remove the impurities. How will you remove the impurities? For this process, my dear students, we take a container like this. Let's say this is a dialyzing membrane. This container is made of a dialyzing membrane. Now what a dialyzing membrane do is, it has such a pore size that it can only allow your true solutions, or I could say the particles which have a size range of lesser than 1 nanometer, to pass through it. That is your colloidal, or if for that matter you have suspension, it will not allow them to pass through the solution. Okay, so this is the basic idea. So if we talk about the dialyzing membrane, let's say you have your colloidal solution inside this dialyzing membrane which has impurities as well. Now impurities are of true solution size, that is crystalloid stands for true solutions, right? Yeah. So now when you will pass water through it, what will happen, my dear students? Ma'am, water will pass. Water is a true solution. It has the size range of less than 1 nanometer. It can go through this dialyzing membrane, yes, and now when it will move past it, it will take the impurity along with it, and since the size range of impurity is also less than 1 nanometer, it can go with the water. And what will you be left with the inside the membrane? You will have only and only your pure colloidal solution. Okay, so this is a method where you can purify your colloidal solution. Now let's read it. The apparatus used for this process is called a dialyzer. The apparatus used for this process is known as a dialyzer. Okay, what is happening? Okay, perfect. Next, the process of removal of impurities from the colloid by diffusion. Now this process is known as diffusion, and you are removing the impurities through diffusion. So this is known as through the membrane is called a dialysis process. Membrane is your animal membrane, parchment paper and cellophane sheet. This is told to you that of what is your membrane formed. Okay, so these are the few things which you need to remember. Whatever is in these slides, you need to learn it. Okay, so I am giving you all the explanation part, but the learning part you have to do on your own, my dear students. So here, but let me tell you, each and everything which you need to memorize is given in these slides. So only and only these slides are to be followed, and you will be good to go for your exams. Okay, perfect. So the apparatus used for the process is called dialyzer. The process of removal of impurities from the colloid via diffusion through membrane is called dialysis. Okay, and what is the membrane made of? It is an animal membrane, parchment paper, cellophane sheet. Okay, if you want to draw this diagram, please do draw this diagram and understand everything very clearly. I hope you've drawn this diagram. Now let's move forward, my dear students. The next method is electrodialysis. So it is not very any different way, only the way that if you want to increase this dialysis process, if you want to increase this process, that is, you need this process to be fast enough, what will you do? Just apply two electrodes, one positive and one negative, that is cathode and anode. Just apply two electrodes, one cathode and one anode, and the process will be faster. The process will be faster. The process is exactly same. Again, you have impurities of the crystalloid size, you have colloid in this, you have a membrane here, you have water here. Water will pass through it, it will take the impurities along with it. The only difference is in electrodialysis, you perform this process in the presence of electrodes, and since you are using electrodes, so the process is a little bit faster. Okay, so the process of dialysis is quite slow. It can be made faster by applying the electric field. This is the major thing to know. Okay, so this is the exceptional thing, anode and cathode. Perfect. Please write it down and then we'll move forward. I hope you've written it. Now, my dear students, the next process is ultrafiltration. Now, what is ultrafiltration? See, generally when we remove the impurities in labs, we use filter paper. Okay. Now, the filter paper's pore size is comparatively large. It will let your colloidal solution or colloidal impurities also to pass through it. It will let them to pass through them. Okay. This is the basic simple. When we talk about the simple filter paper, this is the thing that happens. Okay, but now we don't want that. We want a filter paper such that it will only and only allow your impurities to pass through it, so that you can have your pure solution, that is your pure colloidal solution. And for this you need to make a few changes to that normal filter paper. So what you generally do is you use a colloidian solution. And you need to remember what is a colloidian solution. It is a solution of nitrocellulose with a mixture of alcohol and ether. So what you do is you take the filter paper, you add this colloidian solution all over the filter paper, and then you let it dry, and then the new filter paper which comes to you, that is a modified filter paper, and that has a very small it has a very small pore size, and it will only allow your true solution, that is your impurities, to pass through it, and your colloidal solution will stay up. Okay, so this is how you decrease the pore size of a normal filter paper. So in this method, a special filter paper is used for the removal of impurities. Now that special filter paper is prepared by you add the colloidal solution to it. Okay, so special filter paper is made by soaking the normal filter paper in colloidal solution. And what is the colloidal solution? It is the solution of nitrocellulose and mixture of alcohol and ether, and hardening by HCHO, and finally drying it. Okay, so this is how you prepare a special filter paper, and you use that filter paper for removing the impurities, and this process is known as ultrafiltration. If you use the dialysis process, that is dialysis. If you use the electrodes, then it is electrodialysis. If you use a special filter paper, then it is ultrafiltration, right? Yes, 3 methods we have studied till now. Everything is crystal clear. Please go through it, write it out down, and then we'll move forward. I hope you've written it. These were the only 3 methods for purification. And I hope we have excelled in each 3 parts. You only have to read them from the NCERT now, so that you'll have a better understanding of each and every point. Okay, perfect. Now let's move forward to the next part. The next part is properties of colloids. Now let's try to understand the different properties of colloids. Okay, so when we talk about properties of colloids, the first and the most important comes to be the colligative property. Okay, I hope all of you remember your solutions chapter. I hope all of you remember the colligative properties. Now let me make you explain that particular part. So when you talk about colligative properties, we only say that colligative properties depends on number of substance. That is, if you talk about any colligative property, your colligative properties will only depend upon the number of let's say moles. If you are talking about the moles or anything, it depends on the number. Okay, these properties only and only depend on the number. Okay, perfect. So we say that the colligative properties depend on the number. Perfect. Now let's try to understand a little bit more. Now imagine I gave you two stones of exactly same size. I gave you two stones. You have one stone here, you have one stone here, and they are exactly same size. I told you that convert it into a colloidal range, and I told you that convert it to the crystalloid range. When I talk about crystalloid, you have to understand that I am talking about the true solution range. Okay. Now, you know that the size is from 1 nanometer to 1000 nanometer. And you know that the size is actually less than 1 nanometer. Yes, yes. So here the size range is more and here the size range is less. Let's say you get 50 pieces of colloidal solution from this whole stone. If I talk about the crystalloid range, you will definitely get 100 of it. Let's say 100 or 1000 or how much ever, it will be more than this. Why? Because their size range is more, their size range is small, right? Yes. So definitely they will be larger in number as compared to this. If the number of particles in the crystalloid range are more, and you know that colligative properties actually depend on number, then the colligative properties of your true solution will be more as compared to the colloidal solution. I hope you get this point. That is the point, my dear students. The colligative properties are of small order as compared to that of the true solution at the same concentration. So the particle size is more of colloid than true solution. Then the number of particles of colloid will be less than the true solution, and so the colligative properties are more for the true solution as compared to the colloidal solution. I hope you get this point. Perfect. Please write it down and then we'll move forward. Okay, perfect. I hope you've written it. Now let's move forward to the next topic, which is Tyndall effect. So now let's try to understand what is Tyndall effect. Okay. For understanding Tyndall effect, first you will have to imagine a few things. Now try to imagine, my dear students, you have three solutions like this. This is a normal sugar solution. I have taken water and I added sugar to it and I mixed it. So this is my sugar solution. This is my colloidal solution. I took milk and I added into the water, a very small amount of milk, and added into the water. So this is my milk. You can try this as at your home. It is harmless. Okay. Next is you have suspension. How can you prepare a suspension? Let's take water and add chalk powder to it. Okay. So this is a suspension where you added chalk powder to it. Now, when you will try to pass light through torch or by laser light will make you understand this concept a little bit more. When you will try to pass the laser light through this solution, that is your true solution, you will not see light. You will see light at this point. You will see light at this point and you will see light at this point, but you will not see the path of the light in true solution. Okay. But if you talk about the colloidal solution, you will see the path of light just like I have shown you here. Okay. And if you do the same with the suspension part, my dear students, the path of the light would be even more clearly visible. Okay. Now, why does this happen? Now, let's try to understand this. What happens is, whenever you talk about a particle and a light passes through, let's say you have a wavelength of light, let's say you have a lambda wavelength of light and you have a particle here. Since now, as there is a concept that whatever the size range of this particle is, if the wavelength is of that same order, that same range, then the particle can scatter the light. But if your wavelength range is very high and the particle size is very low, then the particle will not be able to scatter the light. Okay. So for scattering of light, what you need? You need the proper size range for the wavelength, proper size range of the particle and the wavelength, so that the particle can scatter the light. Okay. In true solutions, the size is very small as compared to the wavelength of the visible light. In true solution, my dear students, the size of the particle is very small as compared to the visible light, and that is the reason it cannot scatter that wavelength and you don't see any light here. If you talk about the colloidal solution, the size ranges a little bit more, and so it can scatter the light to some extent. And if you talk about the suspension, then it can scatter even more, and that is the reason we see a better clear path of the light. Okay, so I hope you got the idea of the scattering of the light. Yes, now let me give you a very live example which you might have seen someday or the other. Now let's imagine, let's say that you have a house something like this. Okay, now let's talk about this window. Let's say I am talking about this window and you have sun here. So if you are sitting in the room, then sunlight will be coming from this particular part, right? You can imagine this. You are sitting in a room, you have a upper window, that upper part, and light is coming from that. Okay, if your room is closed, if the inside light is off, then you can see the path of light. You can see very small particles also. That is what is known as Tyndall effect. Your particles are scattering the light and you can see that. That is what is known as Tyndall effect. So the scattering of light which you can see inside the room, that is the Tyndall effect. Okay, so the scattering of the light by the colloidal solution is called the Tyndall effect. I hope you got the idea. Perfect. Yes. So this is how you have been shown that a particle scatters the light. You have a particle here, you pass the light here, it will scatter the light in various different directions. This is a colloidal solution. I hope you're clear with this. Please, you want to draw these diagrams, please draw this and then we'll move forward. Let's move forward. Now you can write these points. The diameter of dispersed particle is not much smaller than the wavelength of the light, and that is the reason it can scatter the light. Okay. Refractive indexes of dispersed phase and dispersed medium differ greatly in magnitude. Okay, these are the few needs that are to be there so that the particles can scatter the light. Okay, perfect. If you want to write these 2 points, please write it down and then we'll move forward. I hope you've written it. Now there are a few points, my dear students, which you need to keep in mind. These are just for your knowledge, that the first microscope, your ultra microscope, was prepared by Zsigmondy in 1903. You might be asked, but there is a very little chance of being asked this question, but still I want you to know this. Next is, it cannot give any information, your particle about the part. Now if you talk about the Tyndall effect, it can tell you that yes, either it can scatter light or it cannot scatter light, but it doesn't give you any information about the size of the particle. Okay, what exactly is the size of the particle? That is something we cannot find out. Okay, yes, so it cannot give any information about the particle shape and size. Tyndall effect is used to distinguish between only and only true solution and colloidal solution. A true solution will not give Tyndall effect, whereas a colloidal solution will give Tyndall effect. This is the only thing that we can find out from Tyndall effect. We cannot find out any more information about the colloidal size particles, their shapes, or what we cannot find, right? Yes, perfect. Please write it down and then we'll move forward. The next property is color. Now let's talk about the color, my dear students. I told you that you have different wavelengths. Let's talk about Vibgyor. If we talk about Vibgyor, then you have these different colors that you can see in the visible range. Okay, now every color has a different wavelength, right? Every color has a different wavelength, right? Now whichever particle will scatter whichever wavelength, you can see that color, right? Yes, so this is what is known, given here. The color of the colloidal solution depends on the wavelength of the light scattered. Whichever wavelength it is getting scattered, you will see the light. If a yellow wavelength light is coming and it gets scattered, you will see a yellow color. If a green colored light is coming and you scatter that, then you will see a green color. So the wavelength corresponding to the particular wavelength corresponding to the particular colored light, you will see that particular light. Okay, perfect. I hope you're clear with this. So you can write this: the wavelength depends on the size and the nature of the dispersed particles. Yes, dispersed particles size actually decides that which wavelength they will scatter. So the size ranges are the most important, which will decide that which wavelength they will scatter, and you will see that particular light. Okay, perfect. Please write it down and then we'll move forward. Now let's talk about the last important point. These are the few points which you only need to keep in mind. You don't have to memorize anything, but you just need to understand these points. Okay, what is a Brownian movement? See, my dear students, your colloidal particles always keep on moving in a zigzag manner. Okay, let's say you have colloidal particles like these, they will keep on moving in the zigzag manner like this. Okay, they will never settle down. They will never settle down. Why they won't settle down? If your colloidal solution colloidal particles settle down, they'll combine together and they'll aggregate together and they'll form a PPT. So in order to remain in the colloidal range, they need to keep on moving. That is, they need to keep on moving in the zigzag manner. That is, they need to keep on showing the Brownian movement. Okay. So this is written here: the continuous zigzag motion of colloidal particles by the unbalanced bombardment of the particles of dispersed medium. Smaller the size and viscosity of solution, faster is the movement. Obviously, you know the particles which are smaller in size, they can move faster. If you have a bigger particle, it will move comparatively slowly. Yes, first thing. Second, viscosity. If you talk about viscosity, what is viscosity? Let's say a particle is moving, the other particle is trying to push it back. That is viscosity. I can just make you understand like this. It is a physics term which you study there, but I hope you can understand. If you talk about viscosity, let's say a particle is moving and the other particle is pushing it back. The resistance to the forward movement is known as the viscosity. Some solutions have a higher viscosity, some have lower viscosity. So if it has lesser viscosity, that is less back pull it is experiencing, obviously the movement would be faster. So smaller size and less viscosity. So smaller the size and viscosity of the solution, faster will be the Brownian movement. I hope you're clear with this. Perfect. It produces a stirring effect due to which PPT does not occur, which stabilizes the colloid. Now see, since they move in the zigzag manner, that is a stirring effect. If this movement stops, if this stirring effect stops, your particles will settle down and they will aggregate together and they will form PPT, which we don't want. We want them in the colloidal range, and for that they need to keep on moving, right? Yes, perfect. The motion is independent of the nature of colloid. The motion is independent of the nature of colloid, whichever colloid it is. Brownian movement will be there in all the colloids. Any colloid that settles down will form a PPT. So, any colloid, the Brownian movement does not depend on the nature of the colloid. Every colloid solution actually moves in the zigzag movement. Okay. Yes. So these are the 4 points, very important for you. You can pause them, write it down, and then we'll move forward. I hope you have written it, right? Yes, perfect. Now we can move forward. Now, my dear students, we will be talking about the charge on colloids. I told you that colloids can be charged. Okay. So now we will be talking about the charge on the colloids, how we can find the charge on the colloids, and this is something very important. Mark it important because question will be asked from this part. They'll give you a colloid and they'll ask you whether it is positively charged or negatively charged. And you have to answer. So for that, you need to listen to ma'am very carefully. So just listen to it. First point is all the metal oxides and metal hydroxides. See, all the metal oxides and metal hydroxides. See, first and most important thing, my dear students, your lyophilic salts, your lyophilic colloids are all the organic compounds. Okay, and since they are stable, they are not charged. They are very stable. They are very lyophilic, are very loving to each other, so they are not charged. We are here only and only talking about the lyophobic salts because they get charged because they are unstable, and now we will be understanding the charges on them. Okay, all the metal oxides. All the inorganic colloids are lyophobic, and from them all the metal oxides and the metal hydroxides will be classified as positively charged. All the metals and their sulfides will be classified as negatively charged. All the metal oxides and the hydrated metal oxides, that is the metal hydroxides, let us say TiO2, Al2O3.xH2O, these all forms will be classified as positively charged. All the metal hydroxides will be called as positively charged. All the metals and their metal sulfides, these are metals and these are their sulfides, all these are not platinum, it should be platinum sulfide or something, so we'll write this. All these are my dear students negatively charged. Okay, next, all the basic dyes, for example methylene blue, are your positively charged. Now all the polysaccharides, starch, gum, gelatin, etc., these are negatively charged. Okay, clay, charcoal, these are negatively charged. Blood is negatively charged, but the hemoglobin of blood is positively charged. These are the few things you need to keep in mind, and this is the part which is most important because question will be asked from this. They'll ask you blood is, please give the charge of blood comma hemoglobin. So blood is negatively charged, but hemoglobin is positively charged, so you need to keep that in mind. Okay, so you can mark important here, just mark it like this so that you'll always remember this. Okay, this table is of utmost importance to you from the exam point of view, so you need to be clear in this part. Okay, so please write it down. I hope you've written it. Now, see, I told you that your colloids can have different charges. It can be positively charged, it can be negatively charged. But how do we come to know that what charge is on the colloid? Is it like we can see that it is positively charged and negatively charged? No, we have to find it out somehow. Now, so now we'll be discussing about a method by which you can see that whether your colloid is positively charged or your colloid is negatively charged, and that method is known as your electrophoresis. In electrophoresis, my dear students, first let's make this correction. This is positively charged and this is negatively charged. Okay, so now let's try to understand it. In electrophoresis, you have a U-tube like this. You connect this U-tube with cathode and anode, that is with a battery. Your positively charged terminal is known as anode and your negatively charged terminal is known as cathode. Always and always this will be true. For electrophoresis, you will have a U-tube, you will connect it to the battery. The positively charged terminal will be your anode and the negatively charged terminal will be your cathode. Now, what you do is you put your colloidal solution here. Now you know that your colloidal solution is either positively charged or negatively charged. Now when you switch on this setup, your colloid is of one specific charge. Let's say it's of positive charge. If it is positively charged, it will go to the oppositely charged electrode. So ma'am, definitely if it is positively charged, it will move to the cathode, right? So if your ion is going towards cathode, definitely it is a positively charged colloid. If your colloid is going to the positively charged electrode, that is anode, then it is negatively charged colloid. So this is how you find out whether your colloid solution is positively charged or negatively charged, by seeing its direction. In which direction is it moving? Okay, so this is the first and the most important method to find out which charge is your colloid. Okay, yes, perfect. The movement of colloidal particles under an electric field is called the electrophoresis. So the colloidal particles movement under an electric field will be known as electrophoresis. The existence of charge is confirmed by the electrophoresis. Which charge is present, that is also confirmed by the electrophoresis process. Okay, you have to write this down, you have to draw this diagram. This is something very important, so pause the video, do this, and then we'll move forward. I hope you've written it. Next topic is electroosmosis. Now let's try to understand electroosmosis. Electroosmosis is very similar to electrophoresis. What actually happens is, you again have the U-tube here. You connect this U tube to the battery, let's say positively charged, so this will be your anode. Let's say negatively charged, it will be your cathode. And you apply a membrane here, semi-permeable membrane. Now this membrane only allows the movement of dispersed medium. This is the property of this semi-permeable membrane, that it will only allow the movement of dispersed medium and not dispersed particles. So when in a process only the dispersed medium can move and not the dispersed phase, then it is known as electroosmosis. So when movement of colloidal solution particles, when your movement of the colloidal particles is prevented by some suitable means, it is observed that only dispersed medium begins to move in the presence of electroosmosis. So if only your dispersed medium is allowed to move and not your dispersed phase or dispersed particles, then that process is known as electroosmosis. Okay, yes, exactly similar to the electrophoresis process. Just the difference is that you apply a semi-permeable membrane and that will allow only the movement of dispersed medium and not the dispersed particles. Yes, perfect. Please write it down and then we'll move forward. I hope you've written it. Now let's move forward. The next topic that we will be discussing is coagulation or flocculation or precipitation. Now let's try to understand this. See, when we started the process, we started the preparation. When I told you that how to prepare a colloid, we studied about peptization. We converted a PPT into colloidal solution. Now we will be studying that. Imagine if you have a colloidal solution and you want to make it, transfer it to the PPT form, then how can you do that, right? Yes, how can you aggregate a colloidal particle and convert it into the PPT? This is what is given here. So coagulation means formation of PPT, flocculation means formation of PPT, precipitation means formation of PPT. All these three words mean exactly the same thing. Okay, perfect. Now the setting of the colloidal particles, I told you, till the point your colloidal particles are moving, they'll not settle down, they'll not form PPT. Once they do settle down, they'll form PPT, right? So the setting of the colloidal particles, that is PPT of the colloidal particles, is called the coagulation. Now let's try to understand that how your coagulation can happen. Let's say you have a particularly charged colloid. How can you settle it down? Ma'am, if I do something and remove that charge or neutralize that charge, it will definitely settle down, and once it settles down, it will be a PPT, right? Yes. So this is our major aim. Let's see. First is electrophoresis. You can use the electrophoresis process to convert it into PPT. Okay, you give so much of the charge, that at one point your charged colloid particle gets converted into PPT, right? Yes, one is this. The other is mutual coagulation. Let's say you have one positively charged colloid, you have negatively charged colloid. They do mutual coagulation, that is, they do neutralize each other and form PPT. That might be possible. Third is by heating. You might heat a colloid and make it settle down and convert it into PPT. That is also a process. Next is persistent dialysis. If you keep on doing the dialysis for a colloid, at one point it will get converted into PPT. Okay, these are the 4 points which are very easy, normal. We know that these are the 4 methods. The most important and complicated part is by adding another electrolyte. Let's say you have a colloidal solution of a particular charge. You want to get converted into PPT, then you will have to give another electrolyte to that colloidal solution, and the charge of that electrolyte will be opposite to the charge of that electrolyte, so that the opposite charges will cancel out each other and you get a PPT. And the most of the questions that are asked are from this particular part. So we will discuss this part in detail. Okay, perfect. I hope you're clear with this. Please write it down and then we'll move forward. Okay, I hope you've written it. Now let's move forward. Now we will be discussing about a very important rule, which is Hardy-Skrut's rule. See, what is Hardy-Skrut's rule? It's not Hardy-Sandhu that you might have heard. It's not Hardy-Sandhu's rule. It is Hardy-Skrut's rule. Please Do focus on that. Okay, yes. So now what actually happens is, in this rule, by using this rule, it told us that we know that an electrolyte can be converted into a PPT. An electrolyte can be coagulated by adding another electrolyte. But which electrolyte will work more efficiently? We'll discuss that. Imagine you have a positively charged colloidal solution. Okay, let's say you have 3 different electrolytes to coagulate it. One electrolyte has a negative of 1 charge, -1. The other has -2 charge, and the third has -3 charge. Which of the following will be the most effective? You'll say, ma'am, more the negative charge, more will be the coagulation, and that is absolutely true, right? So Hardy-Scoot's rule actually tells you that the more the negative charge or more the opposite charge of the electrolyte, more will be the coagulation. Okay, so let's start. Coagulating power depends on the magnitude and sign of the ion. So this is what something important, that how much coagulation will happen, that depends on the magnitude of the charge of the electrolyte and the sign of the charge as well. Okay, let's say you have a positively charged colloidal solution and you add a positively charged +4 charge of an electrolyte. Will it be able to coagulate it? No, you need a opposite charge. So both the things play a very important role. The sign of the charge of the electrolyte and also the magnitude of the charge of that electrolyte. Okay, yes. So the first point is coagulating power depends on the magnitude and the sign of the ion. Okay, the second is, for coagulation of the positively charged, positive sol means positively charged colloid. If you want to coagulate a positively charged sol, obviously you need a negatively charged electrolyte. Now more the negative charge, more will be the coagulation, right? Yes. So this is what is given here. Here 4 negative charges present, so this will have the maximum coagulating power. Then 3 negative, comparatively lesser, then -2, then -1. And if you talk about the coagulation for a negatively charged sol, you need a positively charged electrolyte. More the positive charge, more will be the coagulation. +3, +2 and +1. Okay, so this is very simple. If we try to understand it, it is very common sense that how will it coagulate. Okay, yes. Now let's move forward, my dear students. This is very important. Question will be asked from this part, so please write it down and then we'll move forward. We'll apply all this in the problem solving today only. Okay, so you just write it down. I'll make you understand each and every part. The next part is coagulating or flocculating value. What is coagulating or flocculating value? Now I want to make you understand that. Okay, so for every electrolyte, you obviously have to see that how effective is it. So for that, you need to calculate everyone's coagulating value, so that whenever you want to coagulate a colloid, you can use the coagulating value and find the most appropriate electrolyte for that. Okay, so what is the definition of coagulating or flocculating value? The minimum concentration of an electrolyte needed to cause the coagulation of a sol for 2 hours. So basically, how each and every electrolyte has been assigned a coagulating value. Let's say you have a colloid. Which is positively charged. Obviously, you have some different electrolytes negatively charged. Okay, negatively charged electrolyte, negatively charged electrolyte, negatively charged electrolyte. What you will do is, you will keep on coagulating this particular same amount of colloid for 2 hours with all these 3 electrolytes. Okay, the one which will be able to coagulate maximum of this colloid with the minimum amount of it, means that the one which has the tendency that it is used in a very small amount, but it is still coagulating your colloid to the maximum extent for 2 hours, that will give you the coagulating value or the flocculation value. So the minimum concentration of an electrolyte, the minimum amount of electrolyte used for persistently coagulating a colloid for 2 hours, is known as the coagulating value or the flocculation value. The electrolyte which will have the maximum coagulating value that would have been used minimum amount, right? Yes, with that will have the maximum power, because for a very small amount it is coagulating a electrolyte. This means that it is very powerful. So we say that the lesser the coagulating value, the more will be the coagulating power. The lesser the amount it is used, the more will be the coagulating value. Okay, so this is how. So basically this talks about the amount used. So I can say that your coagulating value actually gives you the how much amount of electrolyte is used. How much amount of electrolyte is used for 2 hours persistent coagulation of a particular colloidal solution. The lesser the amount used, the more is the power. So that is why we say that coagulating power is inversely proportional to the coagulating value. And this coagulating value is actually the amount used. Okay, perfect. I hope you're clear with this. Please write it down and then we'll move forward. I hope you've written it. Now let's move forward. Now the next is coagulation of lyophilic sols. Now my dear students, they are saying that till now we were coagulating only lyophobic sols. I told you that we are only talking about lyophobic sols because lyophobic sols are actually unstable. Okay, yes. But what if we want to coagulate a lyophilic sol? A lyophilic sol is completely stable. Then how can we coagulate a lyophilic sol? Now let's try to understand that. Okay. First is there are two factors which are responsible for stability of lyophilic sols. Its charge and its solvation. I told you that in lyophilic sols you have, let's say you have Na plus, it will be very much stabilized by the solvation process, just like this. Okay, all over the place. So it is very much stable because of the solvation process and the charge. The coagulation can be done by adding electrolyte and by adding suitable solvent. Coagulation can be done by adding electrolyte and by adding suitable solvent. Okay, so now this is completely stable and you want to coagulate this particular very stable colloid. How can you do that? You know that for this particular colloid, this particular solvent, that is, let's say water, is stabilizing it through hydration or solvation, right? Yes. What if I remove this solvent and change this solvent with something else? I can coagulate it. Yes, some solvent which cannot solvate this particular ion, then there will be some destabilization and then it will get coagulated. So if you want to coagulate a very stable colloid, then you need to change two things. One is you need to remove the solvent, you need to change the solvent, you need to add some solvent which will not stabilize it. Okay, only then you can coagulate a lyophilic sol. So this is something very important, that coagulation can be done by adding a suitable electrolyte which can remove its charge, or you can change the solvent, some solvent which is not stabilizing it, then it can be coagulated. Okay, yes, I hope you're clear with this. Please write these points. Now, the next topic is protection of lyophobic colloids. See, I told you your lyophobic colloids are very unstable. Now, since they are very unstable, obviously they will coagulate very easily. I want those lyophobic sols to be protected so that they are not coagulated. Okay, so how can I do that? Just think in a human normal layman language, I can say that, let's say you have a lyophobic colloid. If I have a lyophobic colloid and it is very unstable, I want it is let's say it is of some particular charge positive. Okay, if some negatively charged electrolyte comes, it will definitely coagulate it because it will destroy its charge and it will get coagulated. What if I apply a layer of lyophilic colloid around it? Lyophilic colloid around it. Now what I did, I protected this lyophobic colloid by applying a layer of lyophilic colloid which is actually stable. Now if this is stable, then this electrolyte cannot destroy it. If this cannot destroy it, then the lyophobic colloid will also not be destroyed. So now we have to understand, that this is the best way to protect a lyophobic colloid. Now let's try to understand this. Lyophilic colloids are more stable than lyophobic colloids. I hope you're clear with this, due to the extensive hydration, solvation, hydration. When lyophilic colloid is added to the lyophobic colloid, you added a lyophilic colloid to a lyophobic colloid, okay, it will form a layer around the lyophobic colloid to protect it from the electrolyte. So this lyophilic colloid actually protected it from the electrolyte. Yes, the lyophilic colloids are known as the protective colloids. In such cases, your lyophilic colloids are known as protective colloids, right? Yes, perfect. So this is something which I wanted to make you understand. Please write it down. I hope you've written it. Now, the next is gold number. Now we need to understand what is gold number. Gold number is given to the lyophilic colloids, which protect your lyophobic colloids. How? The minimum amount of protective colloid in milligrams needed to just prevent the coagulation of gold sol by 1 milliliter of 10% NaCl. So basically, all your lyophilic colloids which can act as protective layer are given a gold number. Watching that gold number, you can see that which is a more protective layer. How we can see that? Imagine you have a gold sol and you know that it is a metal ion, that is, it is a negatively charged electrode. I told you metal and metal sulfides are negatively charged colloid. Okay, so this colloid is negatively charged and it is a lyophobic colloid. I hope you know that this is a lyophobic colloid. Okay, so I have to protect this from a 1 milliliter 10% NaCl electrolyte. This is a electrolyte, and this electrolyte is trying to coagulate this lyophobic colloid. I need a very protective layer for it. I know that your lyophilic colloid can act as a protective layer. Now the question is that in milligrams, how much amount of this colloid is required? How much amount of this colloid is required to protect it from this will be its gold number. Okay, so this is the amount. So I can say that the lyophilic colloid which will be used in the least amount, will be the best protective layer. Yes, because let's take an example. Let's say you had a lyophilic, you used a lyophilic colloid, one 5 milligrams and the other 10 milligrams for the same electrolyte, for the same lyophobic colloid. Which is more effective? Obviously, ma'am, the one which is used in lesser amount will be more effective. So the gold number for this would be 5 and for this would be 10. So the gold number 5 is more effective. So lesser the gold number, higher is the coagulating power. Coagulating power is inversely proportional to the gold number. Gold number is actually the amount in milligrams. Easily. Now we can see the gold number of different lyophilic colloids, and we can say that the lesser the gold number, the higher is the coagulating, higher is the protecting power of that particular lyophilic colloid. Yes, because it is telling me that how much amount of that particular colloid is required in protecting this gold sol from this 1 milliliter 10% NaCl solution. Okay, yes. So this is how you compare the gold number of different lyophilic colloids, and you compare that which is the best lyophilic colloid or the protective colloid. Okay, perfect. Please write it down. Then we'll solve a few questions and you will have a better understanding of everything. Let's try to solve the questions. The first question says that whatever we have learned till now, I'll make you apply how you to understand this particular part. The question says that which one of the following sols acts as a protective colloid? Now tell me, if you are talking about a protective colloid, you know that the protective colloid will be stable. And which is stable? Which colloid is stable? Your lyophilic. So basically, by protective colloid, they are talking about the lyophilic colloid. And I know that which of the following can act as lyophilic? All the organic All the organic compounds can form lyophilic colloids. So this is a metal sulfide, and metal sulfides are, my dear students, your lyophobic colloids. Okay. Gelatin is actually a organic colloid. Gold, it is a metal colloid, so it is not stable. Metal oxide, still it is an inorganic colloid, that is, it is a lyophobic colloid. Okay, so gelatin is organic in nature, and that is the reason it is a lyophilic colloid. I told you in the starting that you have colloids of two major types. Either they can be lyophilic or they can be lyophobic. Now these all will be organic and these will be inorganic. And in inorganic, we say that these can be either positively charged or negatively charged. All the metal oxides and metal hydroxides are your positively charged. All the metals and metal sulfides are your negatively charged. These are stable and these are unstable. Okay, this is something which you need to have a clear understanding. Please write it down. I hope you're clear with this. Perfect, my dear students. Let's move forward. Next is As2S3 Sol is. See, it is a metal sulfide, and metal sulfides are, we just studied, these are lyophobic colloids. And in lyophobic colloids also, metal sulfides are negatively charged colloids. Okay, so negatively charged colloids, option B will be your correct answer. Let's move forward. Next is, which of the following electrolyte will be most effective in coagulation of a negative sol? You have a negative sol, you have a negative colloid, so definitely to coagulate it, you need a positive electrolyte, and more the positive charge, more will be the coagulation power. So ma'am, here +1 charge, here my dear students +1 charge, here also +1, and here +2. So the maximum +2 charges here. So D will be your correct answer. So this is how you can find out that which will coagulate best. I hope you're clear with this. Please write it down and then we'll move forward. Next, the minimum amount of an electrolyte required to cause coagulation of a sol is called. The minimum amount of electrolyte required to cause coagulation is known as its coagulation value. It is known as its coagulation value, right? Yes. So option A will be your correct answer. Gold number is for lyophilic colloid, which actually protects them. Okay. So coagulation value will be your correct answer. Please write it down and then we'll move forward. Next question. Next question says that the electrical charge on a colloidal particle is indicated by. Your colloidal particle has some electrical charge. How can you find out that it has what charge, positive or negative? By electrophoresis process. So electrophoresis, option B will be your correct answer. Easy, right? Yes, perfect. Let's move forward to the next question. Colloidal particles in a sol can be coagulated by. You have a colloidal particles and you want to coagulate it. You can coagulate it by electrolytes. Yes. So we can coagulate by electrolytes. Okay. We have heating. Yes. We can coagulate by heating. We studied in the starting part. Adding an electrolyte. Yes. True. Adding oppositely charged sol. Absolutely true. Any of the above methods. So option D will be your correct answer. I hope you're clear with this. Let's move forward to the next question. Next question says that Hardy-Scoot's law states that. What does it state? Let's see the statements. Solution must have higher gold number. No, Hardy-Scoot's rule doesn't say anything about the gold number. Dispersed phase and dispersed medium must be of the same sign. No, it doesn't talk about the signs of dispersed phase and dispersed medium. Micelle coagulate in presence of surfactants. No, it doesn't talk about the micelles as well. The ions carrying more opposite charge to that of the sol particle are effective in coagulation. Yes, that is what Hardy-Scoot's rule says. So option D will be your correct answer. I hope you're clear with this. Please write it down. Next. Given below are a few electrolytes indicate which one among them will bring about the coagulation of gold sol quickest and in the least of the concentration. So you have gold sol. You have gold sol, my dear students. If you talk about gold, you will say that, ma'am, it is a metal, and since it is a metal, so it will be a negatively charged electrode. Sorry, negatively charged sol. So for a negatively charged sol, what do you need? Ma'am, we need for a negatively charged sol a positively charged electrolyte, right? Yes. So let's see which of the following has the maximum positive charge. You have +1 here, you have +2 here, you have +3 here, and you have +1 here. Right, so the maximum positive charge is here, so this will show the maximum coagulation. So option C will be your correct answer, right? Yes, please write it down and then we'll move forward. I hope you've written it. Now let's move forward. Let's talk about another question. The question says that the ability of an ion to bring about coagulation of a given colloid depends upon. The ability of an ion to bring about coagulation of a given colloid depends on the charge. The more the charge, the more will be the coagulation, right? Yes. So it depends on its size, the magnitude of its charge, the sign of its charge alone, both magnitude and sign. Yes, my dear students, both magnitude and sign, because if they will be of same sign, then it will not be able to coagulate it. So we need the opposite sign and also the maximum magnitude. So option D will be your correct answer. I hope you're clear with this. Let's move forward to the next question. The next question says that, and okay, we haven't discussed till now the emulsifying agents. We'll be discussing it. So let's just leave it here. So we'll cover these questions later. With this, my dear students, let's end our session today. So I hope all of you have understood a lot of things today, because today's topic was very important. Most of the questions are asked from the charge of the electrode, the coagulation power, the gold number. These are the few topics which are generally asked in exams. So you need to be very thorough and very clear with these points. I have tried to make you understand through the problem solving as well, also with the theory. Now you have to do, what you have to do is you have to read the NCERT and you have to solve the questions which will be provided to you. Okay, so I hope you understood each and every part. We'll meet in the next session. Till then, keep studying. Bye bye, take care, all the very best.